One
But
should.
you cannot move the cursor.
No, it's a primitive one, but it's fine. I don't need anything. Anything.
Okay.
Right. So, going to close the room.
One
But
should.
you cannot move the
Install my,
cursor.
No, it's a primitive one.
Okay, that sounds good.
2 seconds in Switzerland already. What a conspiracy.
Yes. It's fine. I got a gift.
This way I can buy the one that can also move the cursor.
So it's streaming already?
Yes, we are streaming, we're live.
Hello, everybody. And welcome once more to a .NET Zurich user group session. This time is in person. A bit rushed, but we are here. We got some drinks and food. Later we will have more, even beer. So we are today in the EFK with Shay and Michael. They're doing cameraman. So
Is it working? Maybe we can.
we need the focus.
1 second. Yeah, there we
Oh,
go.
wait. There is another
Oh,
slide,
sorry.
which is important. It took effort to do this. So you have to show it. So it has sound, but it's not fully connected. So let's make like vroom. There's effect. I love it. So first of all, thanks to our sponsors offering solutions, Valve for Texture, our location, Impact Hub Zurich and Stanford Group, and our partners, which is Azure Zurich User Group, .NET Central, .NET AE Switzerland, and Swiss Angular. And of course, thanks Swiss Live, because today we are at Swiss Live. They are hosting this event, so thank you very much. Who are we? Apart from me, there is Powell. Powell, say hi. Yeah. We have Michael. Michael. Yeah. Nigel. Yeah. And then we have Laurent, Fabian, and Mark, which are not here today, but I think it's happy. We are almost half of the team, or more than half of the team, so it's pretty cool. At least the top half, right? That was, what do? We organize events from developers to developers, share knowledge, try to get you excited, networking. Well, not too much today because most of the people here is Swiss Live, but outside we usually do the session, so it's pretty cool. And we had beer and pizza back in 2019 until today. So today, at least we will have beer, later on some wine, pizza, I don't know. I think as we announced it very tight, we don't have warm food. If more people had registered, would be other thing. What can you do? You can follow us on Twitter at .NET Zurich, or also at LinkedIn with the same name, join our meetup group, tell your peers, help us grow, propose your sessions at Sessionize at .NET Zurich. And also you can go to .NET-Zurich.ch and use the hashtag if you publish something which, for example, somebody here I see is publishing something on Twitter, right? As for agenda today, we have laid the reception coffee. We have this introduction, which is what we are doing right now. And then we will have introducing Npgsql. Shay, correct me if I say it wrong.
Perfect.
I practice it because I was, how do you pronounce it?
It's doing very well.
Thanks. Multiplexing, high performance database driver execution model, which we have today, Shay.
It will all become clear.
Yes. He has dared to make this session a bit more generic and open and daring and challenging people. Ask me anything session. Who does that? I think it's quite interesting, quite amazing. Thank you for that. And then we have an upper at 8 p.m., 20 hours. And then we will close the venue about 8:45 latest. So we will have to make sure, Michael and me, that everybody has vacated the venue. Even us. Apart from that, I'd like to introduce Shay. Michael, would you like to do the honors? I mean, Michael is the person that brought Shay here. Should I? Or you want to?
Because I'm figuring out.
Okay, good. So he's still doing cameraman. So what can I say? He's a principal software engineer at Microsoft on the EF team. I think he's not just one more. He's one of the core members of the EF team. And for what I have heard from Michael and Rafi, he is an incredible, not a developer, but architect there. So the abilities in performance, tuning and optimization, I think it's quite amazing. And also he's open source lover, like a lot of us here are, right? So here in SUSE5, we are promoting a lot and pushing out open source. But what can we say with friends like Michael, right?
Very important.
With what they are doing in GraphQL.
Yes.
So yeah, and you are, I think, leading you are the developer lead of the Npgsql.
It's an awful name.
Open source project, which is a .NET Postgres driver for Entity Framework, right?
Not just for Entity Framework, but in general for .NET.
Oh, cool.
And I'll talk a little bit more about that in my presentation, but yes. Yeah.
Michael, careful. All right. So here you have his Twitter account, his LinkedIn. Yeah, the stage is yours.
Perfect.
Thank you so much.
Thank you.
Tommy?
Thank you very much. So I have to do some setup here myself. Yeah, it's actually working. It's actually working. I'm amazed. Okay. So thank you very much. I'm very honored to be here. Also because this is the first. I understood this is the first in-person meeting that you guys are doing. I think it's very important for us to get back to these things a little bit, to also meet in person and not just do the online things. I did a little bit of online conferences and talks as well. By the way, in the EF or in the data team at Microsoft, we do a thing every 2 weeks where we stream. Some of you know this. You're welcome to come and to join us, but it's not the same. It's really, really, really not the same. So I'm really hoping. I know Michael already has his plan full with various in-presence conferences. I've not really started. You guys are actually my first in over 2 years, like that I'm actually going to in person. So it's also important for me, and it's very cool. And yeah, I mean, Michael, we've known each other through the data EF kind of thing for a while, and we've been talking about the possibility of me coming and talking to the group. And I'm very happy that we could finally make it happen. So again, thanks for hosting me and giving me this opportunity to talk about this subject. A few more, yeah, just I'll jump right in. So just a few words to complete Jose's excellent and very flattering introduction. So yeah, my name is Shay Rojansky. I'm half Israeli, half French, but I live in Berlin. It's all very confusing. I can actually speak in German, but I'm definitely not going to do it here, like in this presentation. But maybe with enough beer later, some German might come out. Let's see. So yeah, I'm an engineer on the team. We call it the EF team or the .NET data team, because we don't only do EF core. EF core is the main thing that we do. This is true. Like most of the team is dedicated on working on EF. I'm one of the members of the team that's actually also doing various other things. So one of my interests, I also take care of system data or ADO.NET. That's the lower level API in .NET for accessing SQL databases. So you don't have to use EF core, obviously, in .NET if you want to do databases, right? You can use Dapper, you can use anything else. But anything that goes to, almost anything that goes to a relational database, a SQL database, is eventually going to be using the system.data API in the VCL. That part is also owned by our team, and I do a lot of work on it. It doesn't get a lot, so it's a low-level API that doesn't evolve so much. But when it evolves, I'm usually involved in doing this thing as well. So if you're interested in this kind of thing as well, like why does system data look the way it looks, or what's the history, then I can talk about this as well. Right. I'm not, the team, the EF team, just to present it very, very briefly, where it's not huge. People, it's very interesting. I sometimes ask people, you know what, I'm going to ask you guys, how many people do you think work on EF core? I'm assuming you guys know EF core, by the way. I didn't even introduce, right? No, I mean, you never know, right? This is a .NET crowd, so I kind of assume this, but everybody, okay, I don't need to give an intro to this. Okay. So how many people work on it? 20 people?
Yeah, I would say
40?
40? Okay, so engineers were 5. And in addition to this, there's 1 engineering manager and 1 program or product manager. Okay, so we're 7 people dedicated to, it's not even EF core, but to data. So again, because we're doing other stuff as well. So even this is not fully only EF core, even though it's mostly EF core. It didn't used to be this way, by the way. If you look, I don't know, 5 or 6 years back, the team used to be closer to what you guys guessed, like 20 or 40. There were various changes. It's not that it was starved, you know, people were not fired, but for example, you know, at some point there was a whole testing, dedicated testing team, and Microsoft went a shift where testing is now done by the engineers as well. Anyway, there's a whole history, and I'm actually very surprised by how much we managed to do with relatively few people, I think. So we have 5 people. I'm definitely not special there. So I'm one of the 5 engineers. Each one of us has their own thing. But it's true that one of my main focus points is on performance. That's definitely one of my things in EF Core, but also outside of EF Core, as you will see in this talk. So just to give like an idea. Okay, so yes, there's the whole Npgsql thing, which I will talk about in 1 second, because that's what we're going to be talking about today. So I'm going to dive a little bit more into this. I am a bit special at Microsoft in the sense that I am actually a 100% Linux guy. So I do all my work day to day on Linux. This is my development machine. I use I use JetBrains Rider as my IDE. And my database, the database that I came from, let's say, that eventually brought me into Microsoft as well, is Postgres, which is, everybody here know Postgres, by the way, or at least heard of it. Not all .NET people know about it, by the way. Only the more open sourcey and kind of. So if you're like a Microsoft technology kind of person, it's not sure you will have heard of Postgres. It came from the Unix world. It's definitely a Unix centric kind of database system. It's open source. It's one of the 2 big open source databases along with MySQL, except that it's far better than MySQL. But that's, we won't go into this kind of thing. So I really came from that place of doing, Linux programming, including C and system level kind of stuff. And at some point, involved with Postgres. And then, I did .NET, and the driver for Postgres, was, not as good as it could be. I got involved, and a lot of years later, I find myself like the lead dev and maintainer of this thing, and working for Microsoft, which is super weird. And I'm based in Berlin. I've been there for 3 years, which is also when I joined Microsoft. So 3 years at Microsoft, 3 years so with this. Let's start talking a little bit about what Npgsql is. So if you want to remember, so SQL is obviously SQL, it's a database. Then PG is Postgres. So PGSQL is sometimes the short version for the Postgres database. And then there was a time when, like back in the day, if you wanted to do a .NET library, it was N something, right? Like you guys remember how it worked. Like that was the .NET version of whatever Java thing they were copying. So they called it N. So anyway, that's the reason behind the name. It's a completely open source driver, obviously. I mean, that's nowadays it's not even worth saying. Now, there's 2 things. That's exactly what I wanted to say with Jose. There's 2 things here. There's the low-level driver, which is the ADO.NET or the system data driver, which is what we'll be talking about. The lower level kind of stuff. That's the thing that's responsible for getting SQL from the user, sending it to the database, and getting the results back and giving it to the user back, deserializing it, and all that kind of stuff. It's a very low level, let's say, interface to databases. Usually people will not use that directly, but they can. If you use something like Dapper, then you build on top of this directly. On the other hand, you can also go with a full-fledged ORM, Entity Framework Core in the case, if you use that thing. That also has a driver or a provider, we call it, which is the adapter between EF Core and this specific database, which is Postgres. And that's also part of what I do. So I work there, these 2 levels in the stack. Of course, one works on top of the other, as you can imagine. The EF Core provider works on top of the ADO.NET provider. There are 2 very different kinds of software components. The lower level one is all about networking, buffering, efficiency, doing things, very nitty-gritty kind of down. Whereas the EF Core provider is a lot more high level and using EF Core concepts and stuff like how do you translate link into Postgres specific constructs in SQL. It's very, very fascinating. EF Core is very interesting, but unfortunately that's not my talk today. I could talk about that as well at some point. But by the way, maybe before continuing, so 2 things. We're not that many people here. I'd rather keep this informal, so you guys can also raise your hand at some point, preferably maybe at the end of a slide and not right in the middle. So, but you can really feel free to, let's say, interrupt me a little bit and ask a question if something isn't clear. Maybe I will say that I'll deal with it later, but you don't have to wait until the end in order to ask questions. I'll also do a specific pauses and ask you for, if you have any questions. So I just wanted to say this. Yeah. And also, by the way, so the second hour, this Ask Me Anything thing, this is your opportunity. You can ask any questions about the presentation, but also anything else that I cannot commit to answering the questions. That's why it's not as brave as you made it sound, but I can definitely try anything that's related, especially to data in .NET, Postgres, all that kind of stuff, or even general .NET questions. I can probably field quite a few of them. So I just, a small parentheses. So we're now at talking about the ADO.NET Npgsql driver, the low-level one. Beneath us, there is nothing. So there's no more, there's nothing underneath us in the stack except for the .NET runtime itself. So there's no additional layer. We're already fairly down. If you guys are, working on the GraphQL level, from my perspective, working there, you're way up there, right? You're doing GraphQL, which is in many cases talking to EF Core, not necessarily, but in many cases, and then that's talking to the EF Core provider that's layered on top of me now, like where I am. This is like my perspective on things. So we're going to be talking about stuff that is like how a driver communicates with the .NET runtime and even with the kernel to do things efficiently. That's the level that we're talking about in this talk. And one last comment. So I've been working on Npgsql for quite a long time already. I don't know how many years, must be around 7 or something like this. You would think a database driver, a low-level database driver, is the most boring component, right? Again, takes SQL, sends to the database, brings it back. What could be interesting here? At some point, it just works, right? And then what do? So it's amazing how much that is not true. And I'm still working on very, very, interesting features, still evolving things, still doing perf investigations into it years later. And there's always more to do. It's really quite mind-boggling how that can be, even from something that's so low level and foundational. Anyway, one of the important things when we talk about Npgsql is performance. So I say it's a very high performance oriented driver. And I want to say a few words about this. So what you're seeing here is the results of the TechEmpower benchmark suite, the latest round. How many people here have heard of TechEmpower, out of curiosity? Okay, some people have heard of it. TechEmpower is an industry standard, let's say, a suite of benchmarks of scenarios. There's an organization that runs those benchmarks, and anybody is free to submit an implementation. And basically, it's gained a lot of traction. You have any language and web framework and everything has basically an entry there. So you have all the Java stuff. You have Rust, you have C, you have obviously .NET, you have Go. You have basically everything there is there. The scenarios are oriented towards web performance. So it's typically what happens is it sets up a web server like ASP.NET and it bombards it. And there are these scenarios which you see here, JSON, 1 query, 20 query. There's different scenarios that are supposed to represent different workloads. And we have a standardized kind of form of benchmarking. It's done a lot of good in general to the world, in the sense that you can actually see where you are, and you can use this also to iterate on performance yourself and to profile. It's created a lot of, let's say, especially also inside Microsoft, inside where I work, it's created a lot of, we look at this, we actually care about this, and we try to make it better. So it's kind of like the fact that there's a standardized benchmark suite, it gives you like incentive to work on perf and improve it, and it's quite important. What you're seeing here, round 20 was in February 2021. That's already quite out of date. They haven't done a round since. They are now gearing up for another round, which means that they will run all the latest things with the latest .NET in our case and all that, and publish the results again. This is happening really right now. But what you're seeing here, because it's February 2021, it's before .NET 6, which was released already, quite a while ago. So you're not even seeing the latest results. I hope that in the latest results we'll see even better results. What you see here is ASP.NET Core in 8th place. So that means across all all the frameworks, all the languages, everything, web servers, whatever you want to tweak, all the parameters, we are number 8. And the really cool thing, as far as I'm concerned, is that this is actually running with Linux and Postgres, what you're seeing here. So the high-performing option of using .NET, according as measured on TechEmpower, uses Linux, which is not Windows. Again, we're far away from the Microsoft that 20 years ago. So this is running on Linux, and it's running on a database again that is not Microsoft's database. We're using fully open Linux-centric components here, and we're reaching really the best performance. 8th place is quite good, but it's actually even a bit better, I would want to say. So if you actually research what these things are in the top 10, some of them are, let's say, experiments or personal projects designed to push perf, which is completely fine. That's what it's made for. But I would not call all of these an actual option if you guys are now wanting to start a company and have a high-performing, web thing, you would not necessarily go and use those things. Okay, it's not like a full-fledged, let's say, thing. Not in all cases. In some cases, there are. Actix is a good Rust component. Drogon, by the way, is C++ based. So if you want to write, a web application in C++, be my guest. I wonder how that will go. I'm genuinely very curious. But anyway, the option exists. Interestingly, everything at the top is actually running with Postgres. So if for fortunes, which is one of the benchmarks here, which I focused on a lot, the first time you see MySQL is around place 40. Okay, so apparently MySQL is a slower option in general compared to. It could be that the drivers are of worse quality. That's also possible, but given that everything at the top is Postgres, that's unlikely. You don't see a lot of other databases here for various reasons. With SQL Server, there's licensing issues related to publishing, benchmark results and things like this. So unfortunately, we don't know, or at least I'm not telling you what I know. So really quickly, what the talk is finally about, so we can start going into all of this is more of an intro. So this is about a feature called multiplexing. The word you guys have maybe heard of, but in this context, it means something very specific, which you will understand soon, okay? The feature was introduced right before this round that you just saw in TechEmpower. So it's already been in Npgsql in the driver since November 2020. It's not completely new, but it's kind of experimental. I've not given any talks on this. By the way, this is the first talk about this feature ever, just so that you know, like publicly. It's not well documented, and that's very intentional. So with the idea, I want to productize this and stabilize this for the release in November. So let's say the .NET 7 release will have an Npgsql. Hopefully that will be the point at which I would start recommending to people to actually use it. But if you're a little bit on the bleeding edge or you're really interested in perf, come talk to me. I'm really looking for people, a little bit brave who want to play around with this kind of technology. Other databases do this thing, so I'm not claiming that I'm a genius or I wrote something that nobody has done before. This has been done before, but not in .NET. So if you look at other drivers outside of the ecosystem, you will find very similar concepts, in some cases in very high perf-oriented drivers, let's say. But I'm not aware of anything in .NET that does this, so that's a little bit significant. And in general, the concepts we'll be talking about here, maybe you're familiar, maybe not. If you're not, don't panic. I'm going to go through it very, explain everything. We're going to talk a lot about pooling, connection pooling specifically, what it means to coalesce, to buffer together things, how to do networking very efficiently, and in general, anything having to do with, low-level perf kind of stuff. Finally, I'm going to stop the intro and we're going to start diving into the actual content. So before we start talking about what this new feature is and the hyper thing, I need to spend a few minutes talking about what connection pooling is, why it's there, and how it works. So you have a good model of what every other driver does out there. The basic thing that everybody does is what I'm going to describe before describing the special stuff that Npgsql does. So if you've ever done database programming in .NET, this is system data. This is the standard API for doing database, in .NET. It's not very beautiful. It's not very good, by the way. I try my best to improve it, but this is also a very old API, and you cannot, breaking it is very, very hard. In addition, we're in this specifically bad situation that we have providers. So this is an abstraction, and you have database drivers for SQL Server, for MySQL, for, if it were just an API with an implementation, you can do stuff with it. But if we break anything here, then all the providers out there, which I don't maintain, I only maintain one of them, then they're not going to work. So there's a very high price to doing much more to doing breakage, because this is an abstraction with external providers. That's my life. That's unfortunately how it is. So the model is very simple. We instantiate a connection, a DB connection with a connection string. I guess, has everybody done this kind of thing in the past at some point? Okay. This is not EF core, it's lower level, but still fine. Then you need to open it. That's a very important part. So this is the thing that will actually connect to the database and so on. Then you create a command that has SQL, and the thing that's cut off is the command is connected to the connection. And then you say, okay, execute that command against that connection. This is how the API is structured. And what you get back from this is a reader. The reader is a thing that basically reads the data coming back from the database and provides you with an API for deserializing it and accessing that data. Okay, it's all very straightforward. Now, the problem with this mechanism, if you are naive, is that every time you want to send something to the database, you're going to be opening a new connection to the database. That's a big no-no. So establishing a connection, a physical connection to a database is a very, very slow thing. Okay, you really should never, almost never do it. Typically, you do a lot of small SQLs, right? You send a lot of SQLs every time there's a web request you want to send a SQL. You don't want to open a physical connection every time you do that. So why is it slow, by the way, to open a connection to the database? It's quite simple. First of all, opening a physical connection involves at least one network round trip. Round trips, that means that I'm on my client, the database is over there, I go there, the data comes back. Anybody working with GraphQL, by the way, should be quite familiar with this idea of we want to avoid needless round trips, right? I mean, this is network efficiency, it's the same. It doesn't matter where you are in the stack. We're going to talk about this kind of stuff a lot. So first, there's at least one round trip. Many times there's even multiple ones. If you're using encryption, there's some sort of handshaking that's going to require more than one. I connect and I ask, wait, which encryption schemes do you support? I get the list, then I connect with that encryption scheme. There's a whole handshaking thing going on there. Other databases might have protocols where the connection is even heavier. In Postgres specifically, there's even a worse situation because Postgres is very old school Unixy, from the 70s or whatever. Maybe it's from the 80s, I don't really care. When you create a new physical connection to a Postgres database, it will spawn a full Unix process for you. And then that process is dedicated to you. It's a process per connection model, like we used to do in the old web days, if you guys remember. It's exactly that kind of thing. Of course, if you open a physical connection every single time, it's madness. If the connections are slow, are short-lived. This is the point here. If you have a lot of stuff to do on a single connection, it doesn't matter. If you're repeatedly going to be creating a lot of short-lived connections, forget about it. Okay. So what's the solution to this problem? Like every performance problem in the world, we do caching, right? Like that's the answer to almost every performance thing in the world. And in this context, caching means connection pooling. It means that instead of continuously creating new physical connections, we put the physical connection in the pool when we don't need it, and then we can reuse it afterwards. Okay. This is just a trivial sequence diagram to show you how it works. So we have three actors here: the application, that's us, a connection pool, we'll talk about where it is, and the database, Postgres in this case. So the application goes to the pool and says, hey, I need a connection. Then the pool says, okay, here's the connection. The arrows are like this because these operations are instantaneous. They're supposed to be very short. That's the whole idea. They don't take up time. Then I have the connection, so I can go all the way to the database and ask it to execute some SQL. This takes time. The database is working on execution and finally gives me back the results. Now I'm done with the connection, so I can go back to the pool. That's another explicit operation that I need to do. Here, you can take the connection. Now I don't need it anymore. And then it says, fine. Okay, I got the connection back. The pool, by the way, is also responsible for resetting the state of the connection. Database connections can have state. Maybe there's a parameter, you tweaked it. If we don't think about this, then maybe I put it back in the pool and it has some weird state. And the next guy that wants it, he gets that weird state. That's called a leak, a state leak between the, through the pool. That's a very bad thing. Okay, you don't want it to happen. So there's some more stuff going on in pooling, but I'm not gonna go into it. So I hope all this is quite trivial to people. One thing that is important is the question of where do we want this pool to live? And there's actually several options. This is still a little bit more introductory, but it's important for me. Is everybody seeing okay, or should I turn the lights down? No, it's fine. It's up to you guys. I don't mind either way. So there's several options for where you put your pool. The first option, which is the one that we have in .NET, is you put the pool. Yeah, good. He's going to play with the buttons now. This talk will never continue now because he plays with the buttons. Is this better? Yeah. Okay. We can continue like this.
Just don't log off.
Yeah, exactly. Well, you're not many, so I will see you, and then I will take my revenge. Anyway. The place in .NET for the pool is inside the driver. So it's inside your process, your application's process. The pool is somewhere inside there, and it's inside the driver, okay? So it's, in fact, an implementation detail. There's nothing outside of the driver that tells you that there's a pool. There's no specific API around pooling. But the only thing you do when you open a connection, by default pooling is on, you can use the connection string to say, actually, I don't want pooling for some reason. There are some rare reasons why you might not want pooling. But that's not actually the situation everywhere, just so that you guys know. For example, in Java, you have, if anybody has done JDBC, database programming in Java, then you know there's an abstraction there representing a database connection pool. So the whole thing is a concept in the API, okay? Drivers don't come with their pools. The pool is a separate product. There are multiple implementations, and you can use any pooling implementation with any database driver. So there's a whole different kind of thing going on there. It's pretty cool in the sense that as a driver writer, I don't have to reinvent the wheel every time, right? There's just one pool, and you can use it with any driver. Whereas in the .NET world, SQL client has a pooling implementation, I have a pooling implementation, and the MySQL has an implementation. There is, by the way, like a reference implementation inside the BCL and system data, but I don't use it, for example, because it's not good enough. Anyway, it's like an implement. Let's say there's no real abstraction for what a pool is. This is the thing that I'm trying to say. Now, once I thought this was a really good model, and there's an issue even on the runtime where I thought, yeah, let's design like with Java, let's do a pooling API so that we can do the same thing. At the end of this talk, maybe you will understand why maybe it's not the best idea, but we'll see. There's actually a third option in the Postgres world that's quite strong. A pool can also be an out-of-process pool. So it can be a process somewhere that you connect to, and it does the pooling for you. So it looks like Postgres. You connect to it, you think it's Postgres, you give it SQL, and then behind the scene, it manages the pooling. In most, I think in most, for example, you go to Python, you go to Go, many times you will have this kind of model where the pool, again, is outside of the driver, but it's also outside of the process. And so the same pooling implementation can be used for any language even, right? You can put it in two places. You can put it on the same machine where your application is running, and then it's quite close to an in-process pool. It's on the same server, so fine. Or you can even put it on the side of the database. So that's actually a pretty cool thing when you think about it. What you I'm anticipating a little bit, but the problem, I'll just go down like this. The problem with an in-process pool, like what we have in .NET, is that if you have 5 instances of your application, each one of them has a pool, right? And they're not shared. Each one of them is like a silo of connections, okay? You need to make sure that if all of them can use all their pool capacity at the same time, the database has to, has to withstand that kind of load. So a nice trick that you can do is in front of the database, you can put a pool as well, which is going to be the pool that everybody connects to. And this way you have a single pool instead of 5 segregated ones. I hope you guys get the idea here. So again, the advantage of an in-process pool in general is going to be, it's always going to be faster because it's inside your process. You don't even need to talk to an external process. So if you're really doing a lot of opening and closing of connections, you probably want an in-process pool rather than an out-of-process pool. It's also easier to set up because the pool is just part of your application, right? You don't have to have another process that you need to keep up and another dependency in your DevOps and all that kind of stuff. You can also do both. So a good thing that a lot of people do is you have your Npgsql in-process pool, and it connects to something like PG Bouncer on the server side. A bit like if you guys do you do web servers, then you have this concept of an HTTP reverse proxy, right? It's a proxy that you put, but not a front-end proxy that I have, but it's actually on the side of the server in order to cache. And everybody goes through the reverse proxy. It's the same idea. It's a reverse pool. You put it at the server side, and it aggregates, let's say, across everything. So these are our options of where we want to put the pool. There is one more thing before we jump into multiplexing, and that's the question of what about maximum connections? Do we have a maximum capacity? How does it work? So is the pool infinite, basically, is the question. If you've used various pooling APIs for memory objects, for example, .NET has an array pool, which gives you buffers of memory, which you can write into and all that kind of stuff. Those pools are generally infinite. So you can allocate, you can ask them for as many instances as you want. It will only pool up to a certain amount. It will keep them in memory, but it will never tell you that it doesn't have, that there's a capacity. There's no maximum capacity, okay? I hope that's clear. But with databases, things are different. With databases, it's very important for us to never go over a certain maximum capacity. The reason the reason for this is that every physical connection involves resources at the database side. And you can have multiple applications, again, going to the same database. That's a very, very common setup, right? So if we didn't have a maximum for this thing, then we wouldn't be able to say, this instance of the application will never overload the database above this threshold. And this kind of predictability of resources is very important when it comes to databases. The database is frequently a single point of pressure, right? Of the resources, that's frequently the most sensitive place or point in your entire architecture, right? So to summarize, it's absolutely necessary to have a max pool size and to make sure that your pool will never grow beyond it. So what does happen when somebody wants to create more connections than we've defined? This is called saturation. We've saturated. We're in a saturated state. Okay, we've reached the max pool size. What the standard thing to do in connection pools and database connection pools is to wait. So we can hang around. The open that you saw before is not going to return immediately. Instead, it's going to hang around in the hope that somebody else returns a connection to the pool. And at that point, we can take that connection and give it to you. I hope that much is clear. I've even put a small schema around this just to make sure everybody is understanding this. So John here tells the pool, I need a connection, but now we're saturated. We're in the saturated state. So the pool cannot just give back a connection. Instead, we wait. It's not a loop. Sorry, there's no loop here. There's just a waiting kind of thing. Not sure why there is a loop. And at some point, somebody else, Mary here, is going to return the connection to the pool. And right at that point, the pool is going to hand it off to John. That's how a connection pool works. Imagine, by the way, if you need to implement such a component, it's not trivial how to write something like this. It's very, very concurrency kind of oriented. It needs to be very fast. It's a lot of shared state. I spent quite a bit of time, working on the Npgsql pool around, in my time, let's say. Okay. Let's evolve this model. Up to now was the traditional model. How am I doing for time? Half the time, more or less. Okay, I think it's more or less okay what I planned.
But we have no fixed time limit.
Right. I'll see. We'll improvise, and maybe I'll ask you guys, should I go further or less or what? We'll see. We'll see how it goes. Any questions? Sorry. Yeah.
Yes. So you said the connection pool can be on another machine.
Yes.
But I mean, how can you share the connection if you're not on the same machine as I am?
So the way it works, this is not related to NPGSQL, but it's a process that the front end of this process looks like Postgres. You connect to it as if it's Postgres. Exactly, and it talks the low-level binary wire protocol that Postgres talks. So if you use NPGSQL to talk to one of these out-of-process pools, it thinks NPGSQL is talking to Postgres, but in fact, behind the scenes, it's not talking to Postgres. Exactly like a reverse proxy with HTTP. You talk to it with HTTP, you tell it, I want this resource, and you think you're talking to a web server, but you're not. You're talking to something else that's doing caching in the middle, basically. The same idea, okay?
So you still have the same problem of sharing connection now, just with this proxy in front of you instead of the database, right?
So, I mean, in the traditional model, if you connect to an out-of-process pool, when you open a connection, the driver goes and opens the connection towards that thing. You have now the driver thinks it has a connection. And it does have a connection to the out-of-process pool. When it closes that connection physically this time, at the out-of-process level, that goes back to the pool. I'm not sure, maybe this is not your question. Was this your?
Yeah, I think it's right.
Yeah. So I think I'm actually not, so at my driver, I'm not using pooling at all. I turn off pooling, for example. Yeah. Let's assume I'm doing this. So now every time you do open in ADO.NET in the code, an NPGSQL for you will go and establish a TCP connection. And then at the end, when you do close, it's going to destroy that socket. And so that part of it, yes, you're doing TCP, you're creating TCP all the time connections. And that's why out-of-process pools are not very efficient compared to in-process pools, but you're still not doing it all the way to Postgres. So you're not creating that extra process on the Postgres side and all, you're saving a lot of overhead. And especially if the pool, the out-of-process pool happens to be on your machine, then creating a TCP connection to localhost is not so bad.
Also, then you could use named pipes and other.
You can even use named pipes where the overhead goes even less. Exactly. That's the model that a lot of people use. For example, if you do a Python Postgres, depending what you do, there's many options, but that's a model that you will use many times.
So my understanding was that TCP was the overhead, but there are even other things. Which
There's various overheads, exactly. There's the TCP and the handshakes and all that. Then there's the creation of, on the Postgres side, on the database side, there's the creation of the resources with the connection and all that. Yes, exactly. True. Any other questions up to now about this whole thing? Is this telling people new stuff, by the way? I'm curious. Yeah, you've learned, you're learning a little bit from this. Okay, that's good. I wasn't sure how much of this is kind of self-evident or not. Okay, so let's evolve it. Now we're starting to go into the really interesting things. Don't worry, we'll do it slow. Empty trains. This is my metaphor. I'm going to talk a lot about trains here. So when you look at this code, what you notice is that every physical connection is basically locked for the duration that it is handed out of the pool, right? So let's say I'm a web thing, right? Okay, there's a web request coming in. I ask the pool for a connection. At this point, when open returned, I have a connection instance. It's mine. It's exclusively mine. That's a very, very important point. I can use it for as long as I want. I can send, a command. I can send another command on it. I can send 5 commands on it. And at the end, I'm going to return it to the pool. But during the time that I have it, it's exclusively mine. And that's a very, very important thing. Okay. The problem with this, or let's say the thing that I kind of realized at some point, is this model effectively has us sending out trains. Let's say we're at the train station and we're sending out trains with single passengers. So what's the metaphor? I'm going to explain, don't worry. Whenever I execute a command, you can imagine the connection as a sort of the railway on which we have trains, right? And then the packet, the TCP packet that I sent to the server, or whatever you want to call it, the query that I sent to the server, that's a train. And every time we send exactly one query in there, right? Because the connection, the railway, is exclusively taken up by whoever took the connection out of the pool. So we're sending, we have this big pipe, that's another metaphor, we have a big pipe, but we're underutilizing it in a very extreme way because of the model that we're using, which is connection pooling, okay? How can we make this better? So the idea is to fill trains with passengers. So we want to put more SQL queries or more passengers into the very same train. And in order to do this, those passengers will have to arrive around the same time, okay? So the basic idea behind multiplexing is to say, if we have a lot of database queries or statements that have to happen around the same time, why not put them together in the same TCP packet, basically? Now, notice that these commands are coming from different places in your application, which are not related. That's a very important thing. So we're taking all the unrelated commands happening in a small window of time, and we're shoving them into the same train. That's why I call this multiplexing in my mind. Multiplexing is about, you have multiple producers of queries, and you have to start thinking about this. This is actually about query producers or producers of SQL commands, okay? We have multiple unrelated ones going into one place and being sent into the server together, okay? Now, why would I do this? What are the benefits, the concrete benefits to this? So first of all, you get less TCP packet fragmentation. Now we're low-level networking now, right? Nobody usually thinks about TCP packets. Nobody cares about this. This is like a detail below. But you probably know a little bit about this, at least theoretically. When we're sending out packets on the wire, it's far better always to send one bigger packet up to a point rather than a lot of smaller ones. It's the same principle everywhere in computers, not just with networking. Yes, Jose.
Yeah, that's if I'm not wrong, that's usually called batching. Usually for ASP.NET, when you were implementing an API, usually REST. Sorry, you were doing that to get a lot of requests together.
You're right. You're right. Batching is a word that is used a lot. It also has other meanings. The words here, the terminology is a bit. I don't like to use batching because we usually use batching. So batching, me specifically, usually I see batching as one producer that is sending multiple queries as a batch. So I'm one web request now. There's only one web request. And in order to fulfill it, I need to do one insert and then another insert. So I'm going to batch those two inserts together to avoid the 2 round trips. But there's only one producer. That's how I think of it in my mind. Okay, that's why I don't use the word batching for this, because here we have multiple unrelated producers of queries, right? But you're right. Another word, which is for me more fitting and which we use at the low level, is coalescing. Maybe you've heard about this, coalescing of data. Anyway, you will see in 1 second. I'll go into it. So the idea is, if in the previous model, every controller now in your ASP.NET application is going to be sending one packet. That's the previous model which we saw. Whereas if we do this and we manage to do it successfully, efficiently, then we're going to be taking a lot of these controller invocations together and putting them into a single packet. Every single TCP packet represents overhead. It has headers. It has headers not just in TCP. It has a TCP header, an IP header, an Ethernet header. There's overheads all around. Okay, that's very important. But even if we leave the actual TCP wire layer, there's also the matter of system calls. Every time you go to the kernel and you say, please write this data, you're doing something called a system call. It's a Unixy term. I'm not sure if Windows people use the same term, but I'm a Linux guy, so I'm going to use that term. Going into the kernel actually has a cost. Okay, of course, high-level .NET developers, you never think about this kind of thing. We're now very, very low level. But you would be surprised if now try to do it at home. Go back home. You have a 101, very basic exercise. You need to write 100 bytes to a file. Okay. If you do a for loop and each time you write 1 byte, but really write without buffering it in your application, you really write it 100 bytes, 1 byte at a time, or you do a single write with 100 bytes, you will see that there's a big difference. That's quite a big difference. In fact, the whole Spectre and Meltdown thing, the whole security thing in CPUs, some of the mitigations around these things made system calls also slightly more expensive, by the way. Just so at least that was the situation when it came out. I haven't updated my knowledge about this so much, so it might be out of date. But in general, system calls are something to look at. But the general message is always the same. It's a logic of batching. It's a logic of understanding where your overheads are and trying to do a lot of stuff in one go instead of doing a lot of little things. It's the same idea. Okay. This is what, because I'm going to show you like the big architectural schema. So we'll start with the small one. Without multiplexing, the traditional model, you have the pool. Okay, now I'm talking about how Npgsql is implemented. And inside the pool is something called the idle connection queue. It doesn't matter that it's a queue so much. There is a data structure there which holds all of the idle connections, right? It's very trivial. When John comes, the operation that they do is they rent a connection out of this thing, okay? And then when they're done, they return. And this happens concurrently. Mary is doing it at exactly the same time. Again, even this stuff without the multiplexing is really not trivial to write efficiently. Efficiently being the right word, okay? It's very easy to write inefficiently, but it's not easy to write efficiently and correctly. Okay. Yeah, sorry. Before.
For the traditional model, even there, one thing is that simultaneous thing happening, and but it also needs a lot of telemetry, I think, to tune it correctly.
Absolutely.
And as far as I know, there is no telemetry in Npgsql. So how do you? So
there are some. There is a .NET event counters in Npgsql which report to you about connections being taken out of the pool and being put back in the pool. That's actually existed for a very long time. We'll go back.
I mean, not for the user, but for you as a developer of
knowing.
So you don't know about the usage patterns. Not good enough, maybe.
I guess you're right. I mean, so as the guy who writes the pool, I approach this problem, right? We have multiple, clients, API consumers, and all these two operations need to be able to happen in parallel and very, very efficiently. And you try to solve this problem in various ways. I had a phase where I re-implemented the pool with lock-free programming in order to make sure this. Today it actually uses very little lock-free programming. It's not really necessary. Yeah, it's a tough problem. I'm not sure there's a lot of different usage patterns, which user usage patterns, which make a big difference here, because the API surface is actually very simple. You have rent and you have return. These are the only two operations that a traditional pool supports. You don't need to worry about anything else. But yeah, you're right in principle.
I could imagine that you could optimize for
low usage of connections or saturated state?
You're right. For example, okay, if you go into it, like the more advanced stuff that you do in a pool, usually you want the pool to implement some form of pruning. Pruning means, let's say we had a spike, so now we allocated lots of connections, but now we don't have any more load. So we want to kill those connections. We want to go reduce the capacity. The pool needs to be elastic. What's the algorithm that you use? How do you sample it? What super difficult. By the way, I still don't think this problem is solved correctly, like in the ideal way for all scenarios. Maybe it cannot be solved in the ideal way for all scenarios. But we get a lot of users. This is exactly the kind of complexity that we have in a database drive. You have users who want this kind of pruning logic or that kind of pruning logic. There is a lot of complexity there, you're right. But the basic rent return, let's say, if we stick really to the basic, that's API-wise, like the requirements, the specifications are simple, let's say, relatively. Okay. Any other questions up to now? No. Let's dive into this. So there's a lot of arrows and things. Don't worry about it. I'll go through it simply. So the first thing to notice is that we have the same thing that we had before. There's a data structure here, an idle connection queue, where we have all the idle connections, exactly like before. And exactly like before, we have this guy called John, still renting and returning from the pool. So in this model, you can still get exclusive access to a connection and then return it to the pool, the same thing. But now, of course, we have something else happening as well. And that's the interesting part. What we have here is, for example, Jane, who is now submitting a SQL command into the pool, into something called the command queue. So there's no more rent or return. This is a new kind of operation. Now we are submitting a command into the pool. When the pool receives such a command, it puts it again into a queue, into a FIFO data structure. So this basically is the queue of people who want to get to the database, the passengers in our train station. I'm going to continue with the train metaphor. I hope it helps. So we have a queue of people standing in line who want to get to the destination. What happens now is that we have this. This is the thing that organizes it all. I call it the right loop, the multiplexing right loop. This is the guy managing the train station. It's a bit weird to do this metaphor all the time, but I like it. So I'm going to continue doing it. The right loop, when it sees that there is somebody in the queue, it's going to go to the idle connection queue and get a connection, because we still need to send something over a physical connection, right? So the right loop gets an actual physical connection, and it now has a command and a connection that it can execute the command on. Up to now, everything is quite simple. But instead of just executing the command on that connection, it will go back to the command queue and see, are there more people queued? Are there more SQL commands queued for execution? And as long as there are, it will continuously push those passengers into this train, or serialize that SQL query into the packet, the buffer that is being built up in memory to be sent to the server. All right. Once, let's say, the command queue is empty, then we know at this point we can send that train over to Postgres finally. All right. So at this point, we have the multiplexing batch, and look, I'm using your word. Okay, if even before I didn't change it, so the word is correct. Yeah, we have a batch of commands here. Okay, that has both Jane's and Mary's submitted commands, and this I'll finish and and this gets sent to the database in one go. So that achieves exactly what we wanted, which is to take multiple passengers arriving at the same time and put them into the same train. Yes.
When do you decide when the time your train is
Excellent question. That's a perfect question.
The only issue
You're completely right. So there's two conditions. One I already said, it's very trivial. So it's not even that trivial. I'll say more things about it. Sorry, yeah, I'm making this up as I go along. So the right loop, when it sees that the command queue is empty, at this point, that's a trigger for sending the train, for sending that package. So we're not going to wait around with an empty, train station for another passenger to come in. If we did that, we would be sacrificing latency. It means that all these passengers now are sitting around and waiting, and that means that the latency is worse. It's not as simple as you think. I'll say a word about this in a second. The second trigger, which is just as important, if the empty queue were the only trigger for letting the train go, then under a situation of extreme load, where this thing is constantly full, then we'd never let the train go. right? And of course, we cannot do this. But it's a bit simpler than this. The benefits of doing something like TCP, of doing TCP coalescing, obviously, there's a maximum transmission. It's called an MTU, maximum transmission unit. There's a maximum beyond which the packet is going to split anyway on the network level, right? So if we do 1 megabyte of, a 1 megabyte write, it does not send a single 1 megabyte packet. That does not exist. On the level of Ethernet, by the way, which is one hardware transport, the typical maximum is 1,500, if I'm not mistaken. That's the default in the standard. And there's an extra thing called jumbo frames, which puts it all the way up to 9,000 bytes. Okay. So if you're sure that all of your network equipment supports jumbo frames, you can crank up the NTU on your network card configuration, and you will get a nice bump because you're avoiding all the overheads. This is me talking about low-level stuff in networking and so on. But anyway, this is not very relevant. So there is a tweakable parameter that says once this batch has gone over a certain threshold, send it no matter what, even if there's more people waiting here. And the metaphor here is, of course, the train has a certain size, and you can't put too many people in the train. Okay. It's the same kind of idea. In our case, you can do it, but it will not give you much. And also it will penalize the latency of the first comers. So there's a balance here. I hope you guys understand this. If we wait too much, the more we wait, the more the first guy who came loses, basically. So we want this, we still want the train to go out very, very quickly. Does that answer your question? The first version that I did here, back in 2020, actually did wait around for even when the command queue was empty. I had this idea that we could sacrifice latency for throughput. There's a trade-off here. You could say that if the command queue is empty, we'll wait for an extra 100 microseconds, and if within that 100 microseconds another guy comes in the station, we put him in again.
But then you have a penalty for every.
So how much, maybe you apply that 100 microseconds for the whole batch once, and not every time that a guy comes, you restart the 100 microseconds.
One other question. So is the abstraction that you use still the connection? Like,
No.
This is a new API.
Well, actually, in today's implementation, it is actually the connection. So today, if you download NpgSQL today, I thought to get to the abstraction at the end, but I don't think we'll have time anyway, so I'll say a word now. Today, what you do is you use NpgSQL and you do multiplexing equals true on the connection string. It's a connection string option. Okay. When you do this, connection open becomes a no-op. Yeah. It's a fake call. It doesn't do anything at all. And when you execute a command against that connection, internally that will go and submit that into the command. Exactly. I hope that's clear, but I have other plans for .NET 7. I just went to API review to submit an API that, among other things, is supposed to support this model. So I can talk about this later, but that's really out of scope a little bit. I don't want to make you guys crazy. I want to leave room also for questions, unrelated questions later. Yes.
Just a question about the whole talk. We really talked about how you get the results stream back and do the disposition of the results.
A little bit, not complete. I think you will have a good picture at the end, but if not, ask me the question. Okay, I think you will get it.
The big question is, does Jane and Mary have to take the same train back, right? So that they have to wait until
Exactly. And so now I'm trying to do my marketing and sell all the positive points. But after this, there's the negative. There's the 3 slides with the negative points. You're absolutely right, and you're yes, absolutely. And it's in a certain sense, you already have this problem even with the traditional model. That's my answer to this. But it is less acute. It's less serious than what we were talking about here. But let's continue on with this for a bit. So what we've achieved here is this. Basically, this is the idea behind this this whole model, right? So now, busy trains, just to recap this very, very quickly, the more commands we manage to pack into the same write, the more gains we have, because we've reduced the number of system calls and the number of packets on the wire. Empirically, so I've added some event counters, some diagnostics or telemetry into NpgSQL for this. In the ideal case, when you tweak things exactly correctly, I find that for TechEmpower Fortunes, we can see 23 commands going into a single packet, which is quite nice when you think about it. It's 20 times the, the factor of whatever. So just to give you, this is just empirically measured. It actually works like this. It's quite interesting. But it is important to note, in order for this to work like at this level, like for this to be so efficient, of course, a lot of commands need to be submitted simultaneously. So this is an optimization that affects mainly massive concurrent load or a big sudden spike, right? If you have a lot suddenly coming in at the same time, then we will handle it better. We will improve the perf for you. That's basically the idea. Or if you're running something like TechEmpower, where you really have massive load all the time, there you will see the big improvement in perf. And with that, yeah, there's just one more slide I wanted to because I'm getting to the numbers, by the way, in a second. I know I've been talking about optimization without numbers. It's coming. There's graphs and numbers, but there's one more thing before. I promise you guys just keep on being concentrated. I wanted to compare this with another similar algorithm that all of you use without knowing at the low level. This is an interesting comparison to make. Has anybody heard of Nagle's algorithm or Nagling? Yeah, this is already quite low level. Here I use the word coalescing. Okay, what I've described here, as we said in our conversation, we are doing implicit batching from multiple producers or coalescing. So we're taking bits and pieces and putting them in a single unit. That's what coalescing is about in this context. Nagle's algorithm is something that is done by all operating systems, Windows and Linux, at the TCP stack level inside the kernel. So you're not aware of it. Nagle's algorithm, I don't have a good visualization. You have to look at me. It's very simple. The first time an application wants to send something over the network, Nagle's algorithm sends it over the network, just like that. Very simple. Now the packet is on the way to the destination. Those of you who remember TCP, who know TCP, know that TCP has an ACK that needs to come back. That's how TCP works. As long as we haven't received the acknowledgement, so things are still on the way, Nagle's algorithm kicks in. The next write that we'll send will not go out right away, as long as the ACK has not been received. It will be buffered inside the kernel. And if another write comes in, a third write, it will be coalesced into that thing. Okay? There is a maximum timeout for this, so it will not keep those packets forever. But I don't remember, there's a constant thing. But this is basically the idea. The logic here is that as long as we haven't received the ACK back, the idea here is that we should be able to withhold a little bit withhold the data, not send it right away, because in any case, the other side is still busy treating my first one. That's the logic behind Nagle's algorithm. By default, it's on for all TCP sockets. So if you're doing TCP, you've written any sort of TCP program, you're using Nagle's algorithm without knowing it. It's quite important to understand this. It also can have some negative things. Compared to multiplexing, Nagling works on a single TCP socket. So every TCP socket has its thing. What we do at a much higher level, of course, inside the driver, and we take different queries from different producers. So that's a big difference between what we do and what Nagle does. In addition, Nagle doesn't help with the overheads of system calls. You're still doing a lot of small writes, right? It's only optimizing the networking. I'm just giving you some contrast so you understand the two concepts. In fact, when you think about it, Nagle actually is an algorithm that compensates for a badly written application. Now, I'm saying this, it's streamed live. This is a little bit controversial, maybe what I'm saying, but I think, so basically what I'm trying to say here is this. If you're doing a TCP application, a networking application, you always have to think about buffering, right? It's part of the job, basically, that's your job as a programmer. If you're not buffering at the application level, then usually it means that your application is not well written, except for certain scenarios. So you're supposed to put a buffer in .NET. There's something called a buffered stream. Usually you will have the network stream in .NET, right? That's the stream abstraction over a socket. And above, you will have a buffered stream, for example. And that will be an abstraction that helps you avoid all these small writes. It will buffer together, a lot of small writes. That's what buffered stream does. If you've not used this, or the other way, if you're using buffered stream, Nagle's optimization doesn't do anything for you. You've already done this job in the application. In fact, it only makes things worse because it kills your latency for the second packet, as long as you haven't received the ACK. Yeah, I hope that thing is clear. which is why any efficient network application does this thing, TCP no delay. Npgsql, for example, does this. Any TCP socket that I create as the driver, I immediately tell the kernel, nah, I don't want this, please. Really, I don't need this. I'll do my own buffering. I can do it very well, thank you. Okay. Just be aware of this. This is maybe a point that could be even useful to some people here working on networking. But it's still the same kind of concepts, just working on different levels. Okay, that's why I thought it would be interesting to compare. So we've talked about all the coalescing thing. Wow, yeah. I'm going to take 15 minutes into the. Is that okay? Maybe, I don't know. I'll go a little bit more ahead, and you guys can decide if how long I take into the Q&A.
It's a user group. Take your time, relax.
No, but
If you
still,
need,
I mean, still, the idea here is also to have some time for questions, and I don't want to just stand here and talk. We'll see how it goes. So I promise some numbers. Finally, we'll go for some numbers, okay? And then I'll speed up a little bit. I think you guys will get it. So without multiplexing, I ran all this, by the way, to prepare this talk. I ran everything to get fresh numbers with .NET 6 and Npgsql 6 and all that stuff.
Where do you run the TechEmpower?
So inside, first of all, TechEmpower is an organization, and they have their own hardware, which Microsoft donated, by the way. Yeah, Microsoft does this kind of thing. They have an interest in it. I don't run it there. They only run their own thing, but we have the same hardware inside Microsoft when I have a platform where I can run this much more. This is one of the places where I'm a bit privileged because I work at Microsoft, so I have access to this lab. But
exactly, because there's so many tools you have to run.
So other people who are not inside Microsoft can submit, people do this. They submit PRs to TechEmpower, their TechEmpower, and that actually runs them there. So you can use this. You can actually do continuous runs at TechEmpower. So you can submit a thing, and then the next continuous run will contain the results. So it's not the best developer loop. You don't get like the immediate response necessarily, but you have this option. It's open to the public in that sense. So anyway, it is what it is. But you really cut me off at the most suspenseful point of the whole talk. Everybody's sitting here like this, and you're asking me about. I ran the results again. I ran the benchmarks again, and what I got at the optimal scenario from without multiplexing was about 213,000 requests per second. These are machines which are quite good. They have 14. So the database and the app server are split. It's not the same, obviously. Also the load. So it's a 3-server configuration with one server doing load, one doing the application, ASP.NET, one doing the database. 14 cores. It's a Xeon. It's now a bit dated. It's a bit old hardware by now, but it's still really, really quite good. 213K. By doing multiplexing, that improved by a little bit more than double. Now, that's pretty cool, obviously. I'm very happy to be able to say this, but it's also very specific to this scenario, which is very, very extreme. It's important to understand this scenario sends a query that fetches the results of a very small table, okay? The table is basically cached in memory. So there's no IO happening. The database is not doing actual IO. It's doing only CPU. Also, the latency between the two is it's a very low latency networking. And there's infinite load coming from the client. Okay, that's the optimal scenario for this kind of exercise. So do not expect to get something like this in your actual real world application. All right, but I'll show you now. I will show you why it's not just about the coalescing and that there's other benefits here. So we talked about saturation before and about the whole point of max pool size, right? With max pool size, in the traditional model, the moment I have 100 connections rented out, we block. Okay, and that's the absolute worst thing that you can do is block. That means that the whole thing is now blocked, and maybe we'll time out even at some point. But in multiplexing, we no longer think about connections, and we don't have any exclusive right to a connection anymore. All we do is submit commands, right? Because that's the case, because we've switched the model around in our head, we can continue pushing commands into connections, even though we've already pushed. There's still something outstanding there, okay? Imagine you have the train railway and we've just sent a train. There's nothing preventing us from sending another train on the same thing in the same pipe. So this sometimes is called pipelining, okay? So we're gonna pipeline things when we're at capacity, only when we're at capacity, okay? And we call this overcapacity mode inside Npgsql. To drive the point home, I have some charts. In the normal mode under capacity, as long as we have any idle connection, we're going to prefer sending the commands into that. The right loop is going to prefer using an idle connection. The reason for that is clear. A busy connection is Postgres is busy doing something there. So there's a good chance if we push another command there, it's going to take it more time to get to that thing, right? It's all FIFO. I hope everybody understands. This is all FIFO pipes, right? It's TCP. So I'm going to obviously prefer an idle one where nothing is happening on the side of Postgres, right? But if everything is busy, I can still continue shoving things down that pipe. And there's an algorithm there that knows how many commands we've already shoved, and we're going to go to the one with the least and shove it there. So we're going to try to equalize more or less so that we kind of, we're pushing it down, all the traffic down the pipes. All right, I hope this thing is clear. Now, the advantage of this is that we don't have to wait for the connection to be released back into the pool before we start sending another thing. So in the traditional model, again, 100 connections, they're locked. We can't do anything with them, even though we could have, right? Theoretically, the pipes are there, they're empty. The Postgres is just working on something, or maybe even Postgres is done working on them. And Postgres already sent the results back, and still we cannot send the next query in. That's very frustrating for me as a perf guy, right? It's like all this resource going to waste. So this fixes this problem, let's say. Now, analyzing this, as long as the database is processing the commands fast enough, everything is being pipelined very, very efficiently. We're sending, tons of stuff down the pipe, and Postgres is sending us back the results. As long as this is going well and there's no back pressure, there's no, things are going fast, then this is perfect. Now, if the database starts actually doing a lot of work, has to do a lot of CPU and whatever, at some point, again, this is a TCP thing, there's buffering, there's a buffer inside TCP. And if I start sending more and more and more commands and Postgres is not reading them on the other side because it's busy treating the previous command, at some point that buffer is going to get full. This condition is called the TCP zero window, if people are interested. And it means that my next write is going to block. I'm not going to complete the write. This is, by the way, the only reason for a write call to block. Otherwise, writes are instantaneous. They're buffered, they get sent. Writes are generally an instantaneous operation, unlike read. Read, you have to actually wait for the result to come back. But writes are always instantaneous, unless we've managed to fill all the buffers. Okay. The good news is that even if we get to this state and the write blocks, then we're just back to the way we were in the traditional mode, right? We're blocking, we're waiting. And the moment that Postgres unblocks the whole thing, finishes the query, everything will continue as before. Okay. So that was the second advantage, the better handling of saturation. But now I'm going to turn it around. And now I'm pretty close to done, by the way. The talk is starting to get to the end, which is quite good. So it's very related to this last point. Anybody doing database DevOps always has to ask the question, okay, so how many connections should I plan for? How do you know? That's a very empirical question. It depends on a lot of factors. It depends on, obviously, server resources, how much memory, how many CPUs, all that kind of thing. It also depends what kind of queries you're going to be sending. Are the queries very IO intensive? Or are the queries mostly maybe CPU intensive because the data is likely to be cached in memory? There's many factors here. It's hard to be a real world database guy. I don't have to do this. I just program libraries, so I don't have to care about all these things. But if you really have to manage a real service, then these questions are not easy to answer. Okay. Sorry. Now, the important point here, a lot of people, I had this phase as well. When I set the max pool size, I thought, okay, I'll just set it high enough. Or, I'll err on the side of setting it a bit too high, maybe. This way, I'm sure that I'm not going to get, blocked by max pool size, right? But the point here, and that's important, that's a very fundamental point. At some point, if you're increasing connections too much, then you're asking the database server to do a lot of work in parallel, although it only has limited resources. So what I mean is this. Let's assume that our queries are CPU bound, like they are in our benchmarks on TechEmpower. We're not doing real IO, okay? The database server has 14 cores, physical cores. If we send 40, if we open 14 connections, max pool size 14 connections, and we continuously, send data on it, that's perfect or close to perfect, let's say, because each core is now handling a connection. So it's getting 14 tasks to do in parallel on, CPU. If we send 28, if we do max pool size 28, we're forcing the database server to do a lot of context switching, to pay a lot of overhead for this kind of context switching. That's a lot of CPU work that goes for nothing. You throw it into the garbage. So when you were parallelizing, if you're doing parallelization of CPU bound work, you always have to match it to the number of cores in general. Of course, things are more complicated because work is rarely like purely CPU. It's usually like intermixed with other things. There's lots of factors, but as a theoretical title, that's what I'm trying to make you guys understand. What does this have to do with us? Multiplexing, this overcapacity mode that we just said, actually allows us to reduce our max pool size, because even when we don't have any more connections, we're continuing to send stuff to the database. So in the traditional model, if I put too few connections in max pool size, everything is blocked. Okay, but in multiplexing, nothing is blocked. We are continuously pushing things down the pipe, and even with far fewer connections, we can still push a lot of SQL traffic into the database. Okay, that's the point that I'm trying to say. So what the advantage of multiplexing that might even be more important than the first thing that I talked about, the coalescing and the packet fragmentation, this advantage might even be more important. The fact that it allows you to reduce the number of physical connections that your database actually requires. Okay. Again, this kind of repeats what I said orally. I'm going to show you a graph in a second that shows you how dramatic this effect is. And one last interesting thing about this is that in a way, when you get this, when you really internalize this idea, the pool is actually functioning as a sort of a back pressure mechanism. Okay, it is at the level of the connection pool, we are regulating the the load so that we don't send too much load to Postgres. The idea is to protect the database from too much load, and the instrument for doing this is the connection pool, which is a very weird way to think about the connection pool. That's not the idea behind connection pools in general, right? But that's what we're doing. I want to show some graphs. Okay. So this is just a summary of the benefits that I went through. The first one, I think it was clear, less overhead from TCP packet fragmentation, system calls, and all that. The second two are actually the same, but they're seen in a different way. Number two basically means that we function better under extreme load, which is nice. But number three means that because of number two, we can also reduce the number of connections we actually need. Okay, I hope that makes sense. Okay. Let's go and see the showdown, finally. So this graph shows you multiplexing versus not multiplexing. On the x-axis, you see the max pool size. It's not linear. So if you look closely, you will see here it's 4, 8, and then it's 12, 13, 14, and at the top, we're jumping from 256. This is just a few numbers that are interesting to me specifically. So don't make the mistake of thinking this is a linear. Requests per second here should be pretty self-explanatory. Now, with non-multiplexing, you can see that as we're adding max pool size, we're increasing the number of possible connections. We're getting, of course, here it gets flat because we're increasing by very little, right? Again, because this is not linear. We're increasing the performance up to a peak at 64 connections. So remember, this is a database server with 14 cores. And in order to properly take advantage of it, I need to create 64 physical connections, which is weird a little bit. Right? That's the point I was trying to make. Because the traditional model is not optimized in a way for this scenario. With multiplexing, I can tell you that the peak is at 19. It's interesting. It's not 14, it's 19 for some reason. Fine. But that's an empirical thing, you know. There's other things happening there. There's kernel processes. It's never mathematical in real life, right? This is like a real life, or rather a benchmark, but still. What's very impressive to me is, first of all, how stable this is. Okay, so even as we reduce the connections, we're still seeing very, very close to the same throughput because of the overcapacity mode. So the max pool size no longer really matters that much. That's basically the point that I'm trying to say. And that's an interesting phenomenon, I think. Of course, when we get to 8, then there's a limit. At some point, it's going to be bad. But even at 12, we're already quite close to the optimum. Okay, I think that's a pretty cool thing. Another graph is to plot just for non-multiplexing the RPS, just like before, with the database CPU. It's interesting to look at how these correlate. So on the right side, what you see is DB CPU from 0 to 100%. Here you have the request per second. That's the blue thing. So you can see that as the RPS go up all the way to 64, we have a very lovely correlation with DB CPU, which is showing you that basically here, we're simply not giving the database enough work. That's what it means. And as we're adding more connections, we're able to push more work to the database and thereby improve our RPS. But at 64, something interesting happens. We've gotten to 100% CPU. From this point, if you add more connections, we are over parallelizing. That's exactly the phenomenon that I talked about before. We're now creating artificial, this isn't helping anymore because there's only so much that you can parallelize, and the RPS starts going down because we're starting to pay for various context switching and useless work that we don't want to do. I think that's this graph actually is something to take home, okay, with you in general, like not just for Npgsql or database connections. I'm just going to show the same graph here for multiplexing. The first thing you see is that we never go above 45%. That's just how it is. So the bottleneck here is the application. It's not the database, no matter what we do. That means that there's still more work to be done in Npgsql, in .NET, in ASP.NET, I don't know, but it's definitely not the database. We're not even half of database saturation. And again, you can see that, yes, it does go up, but it's not dramatic, right? We are at 30% at 12 connections, we're at 45% at 32 connections. It doesn't really matter that much. And by the way, when you're here, if you're looking at 256, that's the max pool size. But under the hood, if you actually track the metrics, Npgsql doesn't use 256 connections. It needs far less, okay? Because it always has enough idle connections. It doesn't need to allocate more. Any questions about what you've seen? Or have I just like stunned you into silence?
No, fascinating.
It's interesting, right? Yes. So I do have to say one thing. Yeah, so go ahead.
Do you have some numbers about the network latency resulting in this massive polarization of calls?
I don't. What I can tell you is that I think this is already with 40 gigabit Ethernet and a cable. So there's no switch. Why am I saying this? The idea here is to create super low latency conditions so that the network between that's how TechEmpower does it. It's not my decision. It's really to take that out. So you can imagine that network almost doesn't exist. This is the most ideal situation you'll ever be in. It's almost as if you were talking in localhost, but it's better because it's a different server. So you don't have interference on the same host, of course.
Yeah, because you want to measure the network.
Exactly. And in fact, before we upgraded to 40 gigabits, we were at 10, or maybe I'm confusing now. Now we're at 10, and before we upgraded to 10. The plain text scenario in TechEmpower, that's another scenario, not Fortune's. The plain text scenario doesn't use database at all. So it's really like the web server, the web application returns some text. Minimal work. We saturated the network. We started to be network bound. And if you looked at the public results of plain text, you would see that everybody at the top is like at the same place because it doesn't matter anymore, you know. But of course, who cares about plain text? It's like it's a theory. Even this, so that was my other comment. Don't be too impressed by this, because this is a very I want to say it's a little bit of a synthetic benchmark. It's not a real world situation. There's no IO, the networking is perfect. There's many things making this a very extreme scenario that you're unlikely to have in your real world, and that's very important. So in a way, maybe I'm a little bit optimizing for the benchmark here, but I've also ran various other tests, and the concepts here are still valid for the normal world. Of course, it makes it shine particularly well in this mode, but still, you had.
So in this scenario, you have like one application server and one database, right?
Yes.
So, but like in a real world example of web server, you normally have many web servers and one database. So that's what I see most often. So, I mean, just if you need less connection, maybe less connection per port or per server, per app server, that could all have quite a benefit for.
I agree. I agree with you. And that's why I said before, the fact you can reduce your connection count and still retain the same performance. I'm not even selling you better performance. I'm selling you the same performance, but with less connections, is in itself maybe a a valuable thing. Even more than this promise of you'll get better results. I agree with this.
Why in this platform is the CPU decreasing for 1,000?
That's a good question, and I ran this 2 days ago, and I haven't had time to look into it. Really, I asked myself the exact same question. It could be a bad measurement, but I didn't have time to run this again. It should not. And as I said, in 512, in 512, it's not using 512 connections. So there's no reason why 1024. I agree. I need to. Yes.
I think I don't know, but you just say that it would also be very good to see, okay, how many of these connections are used at that moment. And the other thing I missed here, I would really like to see is, okay, I can imagine that this test is based on the exact same request done massively by the client, right? So you're doing the same request. So if you have as well, how many times does it take at 4 pool size 15 the time, so you have, for example, 50 milliseconds.
I want the latency.
Yeah,
What
exactly.
you want is the latency.
That would be also very interesting.
Sure, you're right. Yeah, this is some stuff is lacking here.
Because I'm pretty sure that these will shine with your strategy, because
The latency.
yeah, because you're like you're matching there, and the others are bound by hardware.
It's a very complex question. The latency question, really. No, it's you're right, and I should. So I have all the data.
At least show the mean latency of the different parts.
So if you guys want, I actually have the results, and I can always as text files. We can JSON files. We can look. Later. No, really. I don't mind. Absolutely.
So what is the queue like to run your stuff on the machine at Microsoft? Is there like I mean, there are other engineers.
Yeah. So there's a whole system called Crank, which is open source and published, written by the ASP.NET Perf guy. Crank is basically a system for doing a perf lab. So you have an agent that you connect to. You have multiple agents on multiple hosts. It ensures that you don't have obviously 2 scenarios running in parallel, because that would be nonsense. So it does all this kind of queuing and the results gathering, and also it connects all the perf counters during your run. Does an average of them, all that kind of stuff.
So you essentially check something in to this Crank, and then you just wait for the results to eventually come back.
It's more like I run a command line that has a lot of switches telling Crank, take this binary from here, run it with this configuration. It runs the command. Usually there's not so much going on. It depends. So I get my results like a minute later.
Okay.
It's really, really cool.
Yeah, because I thought that the ASP.NET Core guys are probably also wanting to run.
So there's continuous benchmarks running on this platform. So there's like a job that every 4 hours runs all of our benchmarks, and the results are published on a public, a Power BI thing, which anybody can look at. And that's how we find our regressions in general in ASP.NET and all that. But you can also manually submit jobs. And in my day-to-day, I don't. Like when I work on this kind of thing, then I intensively submit a lot of jobs. But then, for EF Core, I usually don't work with this. I don't need that necessarily. But yeah, it's very important to have a good performance lab. That's a very
I need access to that.
Someone is busy the next 2 weeks.
It changes. It changes your life. Do I have time for 2 more slides?
Yes.
Yes, you have
Just questions. This slide is perfect to show this. So you've talked about the nagling was the name, and waiting for that knowledge, and usually a good written application should buffer before.
Yeah.
I mean, with multiplexing